Alright, so today we're going to be doing lesson 9.2, which is going to be normal distributions. So today we're really going to be getting into the math that is applicable in statistics. So a normal distribution, more commonly known as the bell curve, reflects symmetry of data with respect to two parameters. So as you can see, this is symmetric, and there's two parameters that we use to create one of these bell curves. We use what we call the population mean, which looks like this is a Greek letter mu, okay? And then standard deviation, also a Greek letter. I believe it's, oh my gosh, my Greek letters are very rusty right now. I think it's sigma, lowercase sigma.
I don't think it's sigma.
Lowercase sigma.
Lowercase, oh, okay.
These are a lowercase.
Yeah.
Specifically, it shows the percentage of data that lies 1, 2, or 3 standard deviations from the mean. Note, a problem must be stated normally distributed for a normal distribution to apply. So in order to use these percentages, you need to make sure they stay normally distributed. Now there are going to be select times where they give you percentages and you're going to use what they give you. But if they don't have percentages, you're going to use these ones. So just make sure you look for normally distributed. That's very important. We won't address that many distributions in this class, but in statistics in general, there's like a bunch of them. So this is what we call the empirical rule. So the empirical rule states that the normal distribution has 68% of its data within 1 standard deviation of the mean. So this is within 1 standard deviation below and 1 standard deviation above the mean. It has 95% of its data within 2 standard deviations of the mean. As you can see here, 2 below, 2 above, 95% of the data falls in that range. And 99.7% of its data within 3 standard deviations of the mean. So 3 below and 3 above. So just to give you an idea of what this means and what we use these things for. You know if you get like scores back from a test and they tell you you're in like the 93rd percentile? That's like, this is what they use to come up with these kind of measures. So that's the kind of things that are utilized here. So we're going to do our first normal distribution curve. So it says data with a mean of 21 and a standard deviation of 4 is normally distributed. Alright, so data within a mean of 21 and a standard deviation of 4 is normally distributed. So the first thing you're going to do is you're going to put the mean in the middle. Okay, that's the first step. The next thing you're going to do is you're going to use the standard deviation to get the other values on your curve. So what you do is you actually, when you go forward, you're going to add the standard deviation. When you go back, you're going to subtract it. So what's 21 plus 4?
25.
Good. And then do it again. What's 25 plus 4?
29.
And then one more time.
73.
Good. And then we also need to go the other direction. So we need to subtract it. So 21 minus 4. Good. Again.
30.
And one more time. 9. So that's how you get the values on your bell curve. Now, we're going to put in our percentages. So what I like to do to make it easy to see is I like to put in these dashed lines. It helps me see where the cutoffs are. And then what we're going to do is we're going to take the percentages from the very first graphic on your notes, the very top, right on the top right, and I'm going to apply them here. So this is 34% of the data. This is also 34% of the data. This is 13.5%. This is 2.35 and 0.15. And then it's symmetrical on the other side, so 13.5%, 2.35%, and 0.15%. So,
where did you get those?
right from the notes, right on the top right of your notes.
Is that what it always is?
Unless otherwise stated, yes, always.
So it's always going to be 34, 34, 13.5, 13.5, and so on?
Yes, as long as it's not otherwise stated. So,
And one with it, and these are, what is it called? The individual ones, like the percentages, like 0.15 to 2.35 and so on. Like, what are those called?
they're the percentage that falls within the mean, like whatever. Basically, 13.5% of the data falls between 13 and 17.
Okay.
They're a representation of what amount of data falls between those categories.
Okay.
So 68% of the data lies between, good, 17 and 25. So the reason that we know this is because 34 plus 34 is 68, right? So 68% of the data lies here in this middle section. And then this is also following the empirical rule. So 95% of your data falls between what?
15
Very good.
and
29.
Good. 13 and 29. So if you added up these percentages right here between 13 and 29, they would add up to 95. And that always follows that rule. 99.7 of the data lies between what?
9 and 33.
Good, 9 and 33. And then you're also going to see these slightly differentiated percentages, so let's talk about that. So 47.5, well, if I add up 13.5 and 34, what do I get? Good, 47.5. So there's actually two scenarios where data falls between 47.5, right? We have from 13 to what? And also and 29. So those are the two situations where there'd be 47% of 0.5% of data between two values. So everybody see what I mean by that? Okay. So the next one says, what percent of the data lies above 29? How would we find that?
adding
Very good. So you're going to add these two up. 2.35 plus 0.15, which adds up to 2.5. And then the percentage of data that lies below 29, 25, how would we do that?
We add everything up.
Good, we would add up all the ones below. Now that's one option. I do want to show you an alternate. Now these percentages all add up to 100, so you could also do the sum of the above minus 100, and either way you're going to get the same answer. So whatever math feels easier to you is fine, and it comes out to be 84% when you do the math. So how does everybody feel so far about normal distribution? Yes? Oh, sure. It's 68%, 95%, and 99.5%. Yeah, it's just the values on the top. Any other questions about example 1? All right, let's try another one. So the heights of 1,800 adults are normally distributed with a mean of 70 and a standard deviation of 2. So 70 inches with a standard deviation of 2. So the first thing we do is we put our mean in the middle, and then we use our standard deviation to tell us where to go from here. So in this case, we're going to be adding 2 each time to go to the right. So this is going to be 72, 74, and 76. And then to get the other side of the data, we're going to subtract our standard deviation of 2. Now we put in our dashed lines, and we copy down our percentages.
So always be these values,
Except
unless
for
otherwise.
unless otherwise stated, yes. And we're going to see one that has otherwise stated. So yes. As long as they say these two words, normally distributed. Because like I said, there are many other versions of distributions in statistics, so they have to tell you which one to use. So I fill in my percentages, and now I'm ready to proceed. And I'm going to show you how to use the proper notation here to write this out. So it says find the number of adults whose height falls between 66 and 72. So how we say that is the probability of falling between 66 and 72. We write it in interval notation. Not interval notation, inequality notation. So x represents the adult falling between 66 and 72. And that's equal to, we add up the percentages between those two values. So 13.5 plus 34 plus 34, and yeah, that's it. 1, 2, yep. So that is equal to 81.5%. But they didn't ask what percent of adults fall between these values. They asked how many. So how could we transfer this from percent to amount? Good job. So what you do is when they want to know the actual number, you're going to transfer your percentage into a decimal, and you're going to multiply it by the total number of people in the sample. And that will give you the amount of people who fall in this category. Something went wrong in my calculator. That was not it. There we go. 1,467. So what they're saying is within the people they studied, 1,467 of them fell between 66 and 72 inches. Does that make sense? Okay. So state the probability that an adult selected at random from a group is more than 72 inches tall. So that's the probability that the adult is greater than 72 inches, which is equal to. We add up all the percentages that are greater than the 72 mark, which are going to be 13.5 plus 2.35 plus 0.15, which is equal to 16%. Now this one I don't need to convert to people because they asked the probability, and we know that probability can be represented as a percent, decimal, or fraction, and it's a percent, so this is totally fine. So any questions so far? What do you think so far? Easy, hard? Good. Alright, so
Wait, was it 60%?
yeah, it's 16. So this is what you've been asking about. You ready? Here's one that doesn't use these values. Okay? So, this one gives you values. So I want to talk about, this is still a normal distribution because it still follows a normal distribution curve, but it's just an adapted curve. Okay? So I'm going to zoom in here so we can take a look at it. So this is female brown bear weights. Okay? The graph gives the weights of a population of female brown bears. The curve shows the weights normally distributed with A. This is the mean. You do need to know those symbols, and this is standard deviation. So, this one gives us percentages to work with. As you can see, the y-axis is percentage of bears. So what you do is you're going to read the axis. So this one falls at 42% based on the axis. I got them exact, so. Good question. If I'm going to expect you to do one like this, I would make sure that there were lines for every one if you were to do it on your own on a test, just to make sure. This would be 23%. 23%.
How would you know these? Like, are you gonna give one on the test where like we have to find the values like this?
Oh, it's from the table. Like I'm reading it from here.
Wait, where?
Like, see, these are percentage of bears, and this falls at 42%.
Oh, okay, yeah, I didn't look, that's my fault.
That's okay.
That's just a 1, right?
It is just a 1, yes. So like I said, I got these exact, but this is kind of one of those things where it's a little ambiguous. You could probably say this is 43, but I would make sure if it's a question on the test or anything like that, that it gives you like more of like a very precise reading. So this is what the setup looks like for this. So now that we have that information, we can move on to the questions. So approximately what percentage of female brown bears weigh between 100 and 129 kilograms? So those categories are this one, and then also this one, right? These three would be between 100 and 129.
Why are the two numbers?
So how this one works is, this is what we actually call technically a histogram. It's not bar graph. Do you remember the difference between a histogram and a bar graph? So a histogram actually has no, it's by category, like a range. So this represents all the bears that fall between 100 and 109. So 23% of them fall in that category. So we're going to add up those percentages. So 23 plus 42 plus 23, and that's equal to 88% of them fall within that category. The next one says approximately what percentage of female brown bears weigh less than 120 kilograms? So weighing less than 120 is going to be these categories right here, right? So we're going to add up those percentages. So that's going to be 42.
Wait, so we follow the one below? Like the numbers below?
These are like the weights. So like these are what weights they fall in. The ones that fall under 120 are these weights right here.
Oh, so it's like 110 to 119?
Yes.
Oh, okay.
Yeah, this is a range of all the bears that fall. A histogram uses range for like each category. So you're gonna like, each range has 10 digits in it, or 9. So we add these up, and we get 71%. Now, this is where you convert. This is basically a conversion part of the problem, where you're converting a non-traditional normal distribution curve into a traditional one in a way. So let's talk through this one. Approximately what percentage of female brown bears have weights that are within 1.5 standard deviations of the mean? So in this case, we have 1 standard deviation of the mean given to us. How can we convert this to 1.5? What if I said within 2 standard deviations? What if I said double it? How would you double it? It would be 20, so it's the same idea. So what you do is you take the amount that they want, 1.5, and you multiply that by your existing standard deviation. And this gives me 15 kg, which you're going to treat like your new standard deviation, okay? So what you're going to do now, like we've been doing on the other charts, is you're going to take your mean, and you're going to add and subtract this number from it. So this is what we call like an adjustment. We're looking at it from a different standard deviation perspective.
So why are you multiplying it by 10?
10 is the standard deviation.
Oh, okay.
So we're taking the standard deviation and we're adjusting it to be 1.5 of that amount.
Oh, okay.
So I'm taking 1.5 of the existing one.
Oh, so that got you 15.
Correct.
And up.
And then you add and subtract it from the mean like we did on the other charts. But we only need to do it once because they only want to know within 1 of that, of each
So
side.
why do we need to add and subtract?
So you know how on all the other charts, within 1 standard deviation of the mean, that could be on the left or the right. So you need to add and subtract that amount to get within 1. It's always left and right when you do statistics. So basically we want to find the probability that a bear falls between 100 and 130 as a weight. So we're going to add up those categories. So that's basically going to be these three in the middle. Now you're not going to add in this one because this one is 130 to 139, which is excluded. So that's going to be 23 plus 42 plus 23, which is equal to 88%. It basically is, yeah. So basically what it's really saying is that A is within 1.5 standard deviations of the traditional mean. Yeah, same thing. Any questions on this one so far? All right, let's move on. Is everybody good with the notes here? All right. So the next one says, for a population of male European eels, always what I wanted to know about, the mean body length and one positive and negative standard deviation is shown below. Sketch a normal curve showing the eel's length at 1, 2, and 3 standard deviations of the mean. So the first thing you're going to do is you're going to take the mean body length, and that's what's going to go in the very middle of your curve. Now they also provided for us 1 standard deviation above and 1 standard deviation below, which means that's what's going to go right here and right here. And with this information, we should be able to backtrack to figure out what the standard deviation is, right? Anybody tell me how we could do that?
Subtract 15.7 from 18.5.
Good. So what we can do to actually find the standard deviation is to take the one above and subtract away the mean. So we're basically just working backwards here from what we did earlier. And that gives me a standard deviation of 2.8. So does everybody see how I got the 2.8? Okay.
You just subtracted, right?
Correct. I just subtracted. So now that we have the standard deviation, we can then keep going. So to go on this side, we can do 12.9 minus 2.8, which gives me 10.1. And then, I think I already have them done, yeah. And then this one will be 7.3. And then we'll go up by adding the standard deviation, which gives me 21.3 and 24.1. Now we are going to add in our dashed lines. And we're going to put in our percentages. And since they didn't give us any, and they said that it follows a normal curve, we can assume that it follows these percentages. So you'll start memorizing these after a while because you use them so much. And you'll also get to the point where, especially if you take statistics, maybe not in this class, we only do like a little brief blurb of this, where you actually won't even write them in, you'll just know if you really keep going with this. So yeah, this would be your answer. This is all they really wanted to know, was a sketch of the normal curve, and then within 3 on each side. So if they say within 1, 2, and 3 standard deviations of the mean, you need to do both sides of the curve. So does anybody have any questions about this one? Okay. So the next one we're looking at is scores on the Algebra 2 final are normally distributed with a mean of, that's an average, by the way. I don't know if you guys remember that, right? Mean is an average. I probably forgot to mention that. With a mean of 150 and a standard deviation of 15. So your mean goes in the middle, and then you're going to add and subtract your standard deviation. So I'm adding my standard deviation, adding it again, and adding it one more time. And then on this side, I'm going to be subtracting it. know I did the math earlier, just double checking my work. Okay. Now that I have that, I can put in my dashed lines and put in my amounts. Just pretend these are straight, theoretically. Okay. So 34, 34, 13.5, 2.35, 0.15, 13.5, 2.35, 0.15. So now that I filled them in, I can continue by answering my questions. What percentage of students took the test scored above 180? So the probability that a student X scores greater than 180 is equal to. How would I find this? Good. So 2.35 plus 0.15 is equal to 2.5%. Because those are scores that are above 180. If 250 students took the final exam, approximately how many of them scored above 135? So we want to first find the probability of the score being greater than 135. And we can do that by adding up these categories, these 5, or 100 minus these 3. So I'm going to add them. So 34 plus 34 plus 13.5 plus 2.35 plus 0.15. And that total comes out to be 85%. But they didn't ask me what's the probability, they asked me how many students. So what would I need to do from here? Good, I need to convert this to a decimal to be able to apply the percentage. So percentages need to be converted to decimals before we apply them, and then we can multiply it by the number of students, which is 250. And we end up with about 213 students. And remember, this is an approximate value. So does anybody have any questions about this one? Is everybody good to try example 6? All right. So the grades on a geometry midterm at Santa Rita are normally distributed with a mean, this is the mean, of 82 and a standard deviation of 4. And one day in this class we will calculate standard deviation. How many students scored between an 85? Oh, let's do our setup before we even read them. So the mean is going to be the number in the middle, and then we're going to apply our standard deviation on both sides. So that's going to be 86, 90, 94, 78, 74, and 70. I'm going to draw in my dashed lines. And I'm going to put in my percentages. So the probability that a student scored between an 82 and a 90, we're going to calculate that before we can calculate how many. So what would I be adding up for this one? Good. 34 plus 13.5 are the only two I'm going to be adding, which I think comes out to be 47.5. So now that we have the percentage, we will then convert our percentage to a decimal, and then we need to multiply it by what? Oh yeah. They didn't tell us how many students there are, so that's kind of useless. Well, we can't really calculate how many then. Never mind. So all we can really give here is the probability, the percentage. They'd have to give you a number of students. So, if Emily scored a 90% on the exam, what percentile is she in? So, we want the probability that x is equal to 90. So, what we would do to do that is we're basically going to be adding up all of the percentages before 90, okay? So we're going to add up all the percentages before 90 because they surpass, basically think of it as like levels in a video game. They surpass all of these levels, so that's like what percentile they are. So you're going to add all of those up.
So would it not be the 2.35?
No, so when you're talking about percentiles, you actually add what's before what we have instead. Because like when you talk about percentiles, somebody's in the 99th percentile, that means they did a really good job. If they're in a low percentile, they did a bad job. So that's a good way to remember it. So if somebody scored a 90, that's a pretty good score, right? So you can add up everything below 90. That's one way to do it. Or you can do 100 minus these two, which I think is a little bit easier. Either one will give you the right answer. And that gives me 97.5%. Correct. It's from the sum of these two, and I took them away from 100. But you could also have, if you wanted to, added up all of those instead, and would have got the same answer. So does anybody have any questions about that using the complement here? Alright, we have two more examples here to do. They're pretty straightforward with the same concept. Alright, where's my clicker? There we go. Alright, so this one says, the amount of soda in a standard can is normally distributed with a mean of 12 ounces, so 12, and a standard deviation of 0.6. So that means we're going to be adding 0.6 on the right, repetitively. And on the left, we're going to be subtracting 0.6. Now from here, we would put in our percentages. Yeah, go ahead. So that's 34, 34, 13.5. 2.35, 0.15, 13.5, 2.35, 0.15. So, the question says, if 250 soda cans were pulled by a company to check volume, how many would be expected to have less than 11.4 ounces in them? So we want the probability that a can has less than 11.4 ounces. So what would I be adding up to get that? Good, 0.15, 2.35, and 13.5, right? I'm adding up everything below 11.4, and that amount comes out to be 16%. So what am I going to do with this 16%? Convert it to a decimal, multiply it by the number of soda cans, which will give me about 40 cans. And remember, this is an approximation, so. So I just want to quickly talk a little bit about, like, we're going to go more in depth about what standard deviation is, but I just want to talk quickly about it. Do you guys know what the word deviate means? Yeah, you deviate from the norm, right? So deviation means like deviation from it, from the norm. Standard deviation means like what amount is standard to be deviating in this particular situation. So that's kind of what this is. I just wanted to talk about what that actually measures. So we'll do the last one. So heights of 16-year-old teenage boys are normally distributed with a mean of 66 inches and a standard deviation of 3. That means that's what the standard deviation is, how much they deviate from the mean, the norm. So we put in all of our values. Everybody's good with that step, right? And then we put in our percentages. $34, $34, and so on. Okay. So if Jabari is 72 inches tall, which of the following is closest to his height's percentile rank? So with percentile ranks, you take all of the values that are below what that height is and add those up, and that would give you the percentile rank. So if you add up all of those, that will be in the 97.5 percentile. So you'll also start to memorize after a while too. This sounds silly, but when you add up certain things, what they equal. Like they're also just you're gonna start memorizing. Another quick tip for everybody, if it helps you with kind of speeding up. This side right here represents 50% of the data. So if you have all on this side, you can do 50 plus these amounts too. That's another way to speed it up.
So in this case, it'd be D.
Correct. It would have to be D. That's the closest one to it if we rounded it. Good.